All right, back in action, guys. So we have already learned a mean value theorem for derivatives, and we just referred to it as the MVT. And it applied to functions that were continuous on a closed interval and differentiable on an open interval, and said that there's always a special x value in an interval from a to b such that f prime of x is going to be equal to f of a minus f of b over a minus b. So there's an x somewhere on the interval where the slope of the tangent line at that point is equal to the slope of the secant line that connects the two endpoints. Now there's also a mean value theorem for integrals, and that's what we're looking for now. So you're still looking at a function, a continuous function f of x, and you are looking at an interval from a to b, and what we're looking for is another special x value, which we'll call c, so that once you find the c, if you find the y value on the curve that goes with that c, and that y value would be called f of c, and then from that y value you make that the height of a rectangle, that the yellow rectangle you draw will have the same area as the exact area under the curve of f of x from x equals a to x equals b. So again, this represents the area under the curve of f of x from x equals a on the left to x equals b on the right. This represents the area of the rectangle. So b minus a is the base width of the rectangle, and f of c is the height of that rectangle. Okay? So if you pick your f of c too low, then the area of the yellow rectangle will be smaller than the actual area, and if you pick f of c too high, the area of the yellow rectangle would be more than the actual area under the curve of f of x. All right, so if we look at this problem and say, all right, the basic idea is that this is area, and area equals base times height. So this is the way I think about it. Then if I divide both sides of the equation by b minus a, I get this equation. So I've just divided the first equation by b minus a. This circled equation is telling you that height is equal to area divided by base. That's the idea of this f of c equals formula. Now, you can put it as 1 over b minus a times the integral, or you can make it integral over interval. And that is my goofball way of remembering average value. Now, when we say mean value theorem, people tend to automatically think about the mean value theorem for derivatives. And so in order to not have to say the mean value theorem for derivatives, the mean value theorem for integrals, because that gets like just wordy, we'll reserve mean value theorem to mean the one for derivatives. And you know, in a math class, the arithmetic mean means the average. So instead of mean value theorem, we'll say average value theorem when we're talking about the mean value theorem for integrals. So mean value theorem will stick with derivatives. Average value theorem then is the wording that we'll use for integrals. So anytime I realize I have an average value question, what pops in my head is integral over interval. Just like when I realize I'm dealing with a second fundamental theorem of calculus problem and DOI pops up, and I think f of high, high prime minus f of low, low prime, all those silly memory tricks help me remember all my formulas. So here's a very, very direct problem, okay? Now, it wants the average value of f of x, and you're given f of x. One of our jobs is going to be to learn the difference between an average rate of change problem versus an average value problem. We're going to be talking about that in the next few days and in the next few examples. But if I want the average value of f of x and you're given f of x, that's average value, not average rate of change. So I see average value, so I immediately think that the average value that they're asking for is integral over interval. So even if I don't write out these words, that's exactly what I'm thinking in my mind. So I remember, how do you get this started? Okay, the integral would be from a to b would be from 0 to 4, because they're giving you the closed interval, of f of x dx over interval. So the interval is the right x minus the left x, and that's how you get the width of the interval. Okay, usually what I do at this point is I say the bottom is just 4, and instead of keeping it as a fraction, let me move it to the front as 1/4. And a lot of times I will combine the step I'm writing right now with the next step in order to burn one step of my writing. Okay, so let's keep moving on. Now I'm just going to apply the first fundamental theorem of calculus. So I know the antiderivative of 6x squared would take me to x cubed, and 6 divided by 3 is 2. And then I'm going to have x squared, 3 over 2. And I'm going to go from 0 to 4. So I have 1/4. Let's see here. When I plug in 4 cubed is 64. 64 times 2 is 128. Plus 3/2 times 16, which I could probably do in my head, but I don't want to do too much in my head and just make silly mistakes on the video. When I plug in 0, fortunately I get 0. That makes it easier to evaluate. So I've got 1/4, and I could distribute 1/4 before I add, which might be easier because your numbers will stay smaller. But let's see here. 2 goes into 16 8 times, plus 3 is plus 24. I think I will distribute first because it might just make finding a fourth a little easier. So a fourth of 128, let's see, a fourth of 12 is 3, a fourth of 8 is 2. So a fourth of 128 is 32, and then a fourth of 24 is 6, and I've got my answer. So 38 is the average value of the function f of x on the interval 0 to 4. So see, it's a pretty straightforward application. So it's important that we know the difference between average rate of change and average value. I'm going to show you something and then erase it. Okay? If you are given velocity, for instance, and you were asked for the average acceleration, okay? Remember, acceleration is a derivative of velocity. And whenever I want to approximate derivative, that's when I do slope formula. This is then average rate of change. Because remember, the relationship between acceleration and velocity is that the acceleration is the rate at which velocity is changing. Okay? If I were to ask you for average velocity, all right, if I give you velocity and ask for velocity, then you're dealing with an average value problem. And that's when you skip into integral over interval. So I've abbreviated there. So that just takes some time for you to remember or realize which one you've got to do. They're both very, very quick. They're not difficult problems on the AP exam, but they do expect you to read the problem and realize which one they're asking you about. And that can be tricky, especially when you're just brand new at this stuff. Okay, so there's my little spiel on one versus the other. So this is, again, I've just picked out AP problems that that we've done before that I need to make sure you've got some exposure to. So this being number 1 means it would have been a calculator problem, so you'll see me use my calculator. In fact, it might be smart to go ahead and put this function f of t in y sub 1. So I'm going to get my graphing calculator out. I hope you do too. and I've got the intervals 0 to 30. So let's see here. On my graphing calculator, y sub 1 will be 82 plus 4 sine. Double check, make sure your calculator's in radian mode. And t over 2 is just x over 2 because your calculator doesn't know if it's a t or an x, so don't worry about that. Okay? If we need to graph, then I'll put in the 0 and 30 as my x min and x max. That may not be an issue, so I'm not going to overdo anything yet. All right, so on this problem, part C says, what is the average value of the traffic flow? Well, I don't know if that's average rate of change or if it's average value. I think it's just average value because it says that. Look at part D. On part D, it says average rate of change. So f of t represents traffic flow, and the flow, it says, is measured in cars per minute. So this is traffic flow. So what's the average value of the traffic flow? Okay, so when it says on the interval 10 to 15, so I know on part C the average value is the integral over the interval, and the interval would be 15 minus 10, and the limits of the integral are 15 and 10. So that's always going to work out that way. Of what? Guys, just write f of t dt. If this is a calculator problem, then there is no reason for you to spend a bunch of time working this out. Once you set it up and you say, this is what I'm going to calculate, you can do the rest on your calculator. And we've already put this on our calculator. So what I'm going to do is I'm going to use my function integrate command. So I've got the equation in my calculator. Let me quit and go to my home screen. Okay, so I want to go to math, and let's see here. Choice 9 is function integrate. So I want to integrate from 10 to 15 of the equation that I put in y1, so variables, y variables, no matter where I put this recording button, function y1, no matter where I put the I don't know if you can see my recording button, but I keep having to move it around. All right, so I'm going to go ahead and hit enter. Now remember, that's the integral. I need to divide by the interval width. From 10 to 15 was a total of 5. So I'm getting 81.8992. So this is 81.8992. Now we need to interpret that, and it says indicate units of measure. So I'm going to indicate units of measure when I interpret what's going on. So that means on the time interval, (10 to 15 minutes), there was an average of about 82 cars per minute flowing through the intersection. So since it's the average value of traffic flow, then I'm going to use the same units of measurement as traffic flow was given. All right, so on the second one, what is the average rate of change of the traffic flow? So on this one, average rate of change, a rate of change means a derivative, right? So if we approximate the derivative, f prime of x is approximately equal to f of b minus f of a over b minus a. So the average rate of change would be, and again, we're using 10 and 15, f of b. So I better use f, capital F of b, minus capital F of a, all over b minus a. So again, set up the original problem because you have to declare what it is you're calculating so that you don't have a bald answer. So big F of 15 minus big F of 10. Okay, so let's do this. I'm going to do this on my calculator. So big F of 15 would be y1 of 15, and you could also do this with your table feature, minus y1 of 10. Okay, so that gives you your f of 15 minus f of 10. You don't have to do anything else with it. And then remember, that was over 15 minus 10, so over 5. So I'm getting 1.5175. 1.5175. Now, on this one, if you do a derivative, then it would be cars per minute per minute. So cars per minute squared. So it's saying that that between the time of 10 and 15 minutes, that the traffic flow was increasing because it's positive 1.575 at a rate of 1.517 cars per minute per minute. So traffic flow is getting heavier on that time interval. Okay. Now let's look at another average value problem, which actually gives you a nice review of things earlier in this chapter. So it gives you a table, and it says the temperature in degrees Celsius of the water is given by W. So that's in the right-hand column of the table. And it depends on time. Time is given in the left-hand column of the table, and it says that you see time over a 15-day period every 3 days. So it says approximate the average temperature. Well, again, since we're given temperature and it asks for average temperature, this is average value, not average rate of change. So I want the average temp. That's average value. So I'm going to do integral over interval. So the integral, and it says go from 0 to 15. So the integral would be 0 to 15 of W of t dt over 15 minus 0. All right, but we don't have an equation that we can find antiderivatives for. So how are we going to do it? It says you're approximating. Oh, if you're going to approximate an integral, guys, that means you're going to have to do a rectangular or trapezoidal. And look, it says a trapezoidal approximation, and it says with subintervals of length 3 days. So that means one of your intervals will be from 0 to 3, one will be from 3 to 6, one will be from 6 to 9, 9 to 12, 12 to 15. I didn't do that very well on that one. So I'm going to say 1/15 times the integral. And let me say approximately here because now I am going to start to. So 1/15 times, and I'm going to have to do the area of 1, 2, 3, 4, 5 trapezoids. So the first trapezoid has bases of 20 and 31. Remember, the y values are actually the bases. So average your bases times your height. Your height's from 0 to 3, which is 3. Plus, your second trapezoid has bases of 31 and 28. Average your bases times your height. Your height's always going to be the delta t of 3 days. So that's going to be consistent. Your third trapezoid goes from 28 to 24. Times your height. Your next trapezoid goes from 24 to 22. Times your height. And your last trapezoid goes from 22 to 21. Times your height. And then don't forget to close. Now, remember, that number 2 would also be a calculator problem. So you could just start working on your calculator for the rest of that. Let me give you a little hint. On the AP exam, if you are done at this point, once you've got it set up to where it's nothing but a numerical expression, all you'd have to do is add, subtract, multiply, divide, nothing else. Like it's not the same thing as having to take the tangent of or the square root of. But if you get down to where it's just add, subtract, multiply, and divide, you can actually stop. And that way you will get full credit for your answer because you've completely shown with nothing but numbers what you would do only on your calculator from here on out. Okay? So there we go. That's your average value portion of the lesson.